Okay, we'll go ahead and get started here. This is hopefully going to be a short video covering the alpha antennas Hextenna, my XYL KC3JAS, and I've been using this antenna for over 5 years now, and thought we'd put together this video, talk a little bit about the way we do the setup, and then some maintenance items. Just generally speaking, we've had excellent performance with this antenna over the years, and just wanted to pass along some things we picked up along the way. A little history about the antenna. We purchased it at Hamcation in 2020. That was right before everything blew up with COVID. Prior to this, we owned an Alpha FMJ vertical antenna from Alpha Antennas, so I was familiar with the company, liked the performance of the FMJ antenna, and when Judy saw this antenna at Hamcation, she got excited, I think because it was shiny and looked neat. I got excited when I saw it, because what it is, it's an infinitely variable length dipole, and I knew with that I'd be able to just adjust the resonant frequency on any band exactly where I wanted it. So we bought it and started using it. Since then, we've had over 500 deployments. Most of those were POTA activations. Judy's a POTA fanatic. We're out every weekend, sometimes for whole weekends. Take road trips, and just she has to get her POTA fix. Operating locations, most of our operating is in Pennsylvania. We live in north central Pennsylvania. She's also been to Ohio, Indiana, New York, West Virginia, Virginia, North Carolina, South Carolina, Georgia, Florida, Louisiana, and Ontario, right on Lake Erie for a POTA get-together up there. So we've been in quite a few different places, and I'll talk about that a little bit later, about my thoughts on ground effects. And as a note, we've only operated this as a dipole. There is a way you can set it up as a vertical, but we haven't done that. So the first thing I wanted to go over was Hextenna tuning. Anytime I have a change to the antenna, I'll do a retest using my Rig Expert AA54 and the AntennaScope software, and just to make sure everything's where I think it is in terms of the overall lengths for each band and the resulting resonant frequency. So the last time I did this was appears to be May of 23, when I had a damaged feed line that I replaced. And just to note, all of the measurements shown are from the end of the feed line, so the feed line is included with the data. This is a look here at 4 of the bands starting at 40 meters. This is a standing wave ratio. And what I wanted to do was to put the resonant frequency right in the middle of the extra single sideband range. And the reason for that is Judy operates exclusively on single sideband for POTA activations, and I wanted to get that right in the center to give her the best overall SWR through the whole range. And as a point of reference, this is 1 on the SWR plot, 1.5 and 2. So you can see here we're generally at or below 1.5 through the whole 40 meter band, and when we're near the resonant point, we're down to about 1.2. Similar results for the 20 meters, 17 meters, pretty narrow band. We've got it centered right there, and then 15 meters, you can see we've got it centered there as well. So we've got these 4 bands pretty well dead nuts where we want to have them to operate. And then this is a look at the remaining bands, the 12 meters. Very good range here. 10 meters. And then the 6 meters, my analyzer runs out of juice at about 54 megahertz, so I don't know what's going on there. But we can operate 6 meters effectively. Now, as a result of these measurements, what I do when I get the resonant frequency where I want it, I measure the overall length of the element and record it for each band. So you can see that's what this green column is here. And then the fully extended length of the Hextenna element is 213 inches. So then I compute another column here, which is if I fully extend the element, how much do I have to shorten it to get to this length? So it's just a matter of subtracting the overall length from 213, and that tells me how much I need to shorten it. So, for example, to go to 40 meters, we need to fully extend the elements and then shorten it 16 inches. And then you put the wire element extenders on for 40 meters. 20 meters, same thing, extend full extension and then shorten it 12 inches, and then you've got the shortening lengths for each of the remaining bands. Now generally if I get down to, if I go 17 and higher, then I just use the overall length, but I've got a little video I'll show you on how we do these adjustments here pretty easy, and it's very easy to go from 20 to 40 without dragging out a great big tape measure. So we'll see if I can get this video started here on how we adjust the elements, and hopefully this will work.
Okay, now I'm going to take a look at how I adjust the elements for the different bands. We normally start on 20 meters, and from the table of the measurements that we worked up, I know that I have to shorten the element 12 inches from the fully extended position. So what I do is I start with the element closed all the way down, and then I open this with the corona ball here on this end. I'm going to open this up all the way, and when I look at that dimension, that is, get my handy dandy tape measure out here, you can see that that's 20 inches. Slide that down. So you can see that that's 20 inches long. And according to my table, I need to shorten this 12 inches. So the way I do that, here's the 12 inches. I'll take, let me hold on to this so it all works. I'll take this element and push it back in beyond the 12 inches. And then I'll pick up the tape measure, stick my thumbnail right there on 12 inches, and then place that beside the corona ball and pull it out. And there it is. That's 12 inches shorter than the full extension. Do that to the other element. And then I take it out to the tripod with the hub on it. Fully extend the elements and then screw them into the hub. A couple little tricks on the elements I found is that you want to make sure when you're extending them, you want to hear kind of a good solid click, making sure you have full extension. The other thing on closing up the element to protect it a little bit is, rather than just trying to push it in, I like to rotate it a little bit and push it in, and it goes right in, and that gives you, you don't put as much stress on the element, particularly more important with these thinner sections of the elements. So you want to hear that pop at each extension as you extend the antenna, and then just twist it a little, each element, as you close it up when you're done. And that's pretty simple. Then when we go from 20 to 40, the table tells me I need to be 16 inches shorter, and then clip on the 40 meter elements. So So the way I do that, being inherently lazy, rather than just to make it real easy, we'll have this element out here. This one's 12 inches shorter now because it was on 20 meters, so I take 4 inches. I'm going to shorten this thing 16. So I just take my little tape measure, mark it at 4 inches. It's usually easier when you're not trying to do this with a camera. And then I just slide that down, and there we are. So then all you do is clip the alligator clip on here and extend the element extension, and you're on 40 meters. So it just takes a couple of minutes to go from 40 or 20 to 40. And then I found the other dimensions, the other bands. I just measured the overall length and adjust to that, right? Because the trying to shorten it, the amount that you would need to shorten it to go to the higher frequency bands is just a bit cumbersome. So that's how we do the elements.
Okay, now we're going to move on to a topic on the ground effect of the Hextenna, or any antenna, particularly dipoles. And I don't want to point out, this is just my not so humble opinion. It's also my current best theory on what's happening with the antenna and the effect of different types of grounds. So just a quick review. If you're not into all the math and stuff, bear with me. You can fast forward, I guess. But just as a review, what I wanted to do was go take a look at the reactants, both capacitive and inductive reactants, and how they behave as a function of frequency. So you probably saw something like this in the general class study that you did, and certainly in the extra class if you went that way. But if what this is telling us is that the capacitive reactance as a function of frequency decreases as the frequency increases. So it becomes more and more lower impedance reactance as your frequency goes up. Then the inductance behaves in the opposite direction, in that it'll linearly increase as a function of frequency, and the higher the frequency, the higher the inductance. And the convention is that inductive reactance is positive and the capacitive reactance is negative, and the total reactance of a series circuit is the sum of those two. So there's a point where the capacitive reactance equals the inductive reactance, and they completely cancel out. So there is no reactance, and all that's left is the real resistance of the antenna. So this is how the resonant point is defined, at the point where the capacitive reactance and the inductive reactance equal and cancel each other out. And that's the point that we're wanting to put exactly where we want to put it on the band that we're tuning the antenna for. So this concept of resonance is a real key to understanding how to tune your antennas and what's actually going on. So let's go back and take a look at the 40 and 20 meter charts we just looked at. And what will happen is we've got the resonant frequency set about here, right in the middle of the single sideband range. Now in Pennsylvania, just about every hill that we've been on to set up an antenna seems to have pretty much the same geology. It's a layer of gravel on top of solid rock with about a half an inch of topsoil on the top of it. So it's pretty consistent. That's the structure I have in my backyard where I do my antenna tuning, and this is where I got this set point, just measuring these frequencies out in the backyard. Now, what will happen if you go to a different type of ground, say it's a big thick layer of topsoil, and the capacitance is going to be different. Say it increases the capacitance due to the coupling of the earth to the antenna, it'll increase the capacitance of the antenna so that you have to go, which also increases the capacitive reactance, which means in order to find that resonant point, you'll have to go to a higher frequency and find the point where the capacitive reactance cancels out the inductive reactance. So what in effect it'll do, say if we go to a higher capacitance ground, it'll take this resonant point and it'll just shift this whole curve up this way. So if you just imagine that happening, and then your resonant point is right up here, let's say. Now if we took this curve and shifted it up to here, then it would look something like this, and you would still have a pretty low SWR, even with a pretty significant shift in the ground capacitance based on the soil type that you have. And that's because this SWR plot is nice and flat, and if we move it, then we still have pretty good operating conditions. Now if you use, let's say, some sort of antenna that has a trap in it, where you're trying to get a shorter antenna with the resonant frequency, you'll get a resulting change in bandwidth of the antenna for the SWR to look something like this. And you can imagine if you shift this curve to the right, because it's on a different type of ground, you're going to very quickly start getting into your higher SWR readings and start affecting the performance of the antenna, because the grounds are changing the capacitance, and you're getting just shifting that curve this way. So I think what we've observed with all the different places we've been is that we really haven't noticed any performance differences due to ground variations. And I think this is the reason why, like I said, this is my current best theory, is because we have such a nice flat SWR, being a true dipole, that the changes that might be induced by changes in ground don't really adversely affect the performance of the antenna. And that's why sometimes if you have a compromised antenna, you may see the ground effects impact your performance. So I haven't done any measurements on different grounds, but this is just kind of an eyeballing of what we found. Never really seen any problem with changes in the ground that we noticed in the operation of the antenna. Okay, now we're going to take a look at hub mounting. Got some ideas here. No great eurekas or anything like that, just some little tips we've kind of stumbled on as we moved along the POTA path. So let's see if I can get this started. I'm not only am I an amateur with radios, I'm an amateur with videos too, so just bear with me. I'll get it going here and hopefully it'll work.
One of the concerns I had with the hub is that if you install this thing so that everything's tight here, when you screw it in, and then you lock your antenna elements in here, this, and they're extended out on both sides. All the movement from the antennas in the breeze will concentrate stresses in this hub at this point and here and down in here, and then the constant flexing as you use it can lead to failure. You get fractures either at these points here or down here. So what I did is I took, this is a 24-inch shock cord, and when I attach the hub, I don't tighten it down all the way. I tighten it down and then bring it back open a little bit. Then I take this shock cord and I line the space of the hub up with two of the legs of the tripod, and I stick them in here like this and hook them. And then I pull the shock cord up here and bring it over this top element, making sure that the shock cord goes over the shoulders of the hub. And what that does is it gives you a little shock absorber effect so that this can move, and it gives you the ability to dissipate some of this energy that's going to be coming in from the antenna elements moving in the breeze. It'll dissipate that energy into the shock cord, acting as a little bit of a shock absorber. That's rotational, a little lateral movement there, and that takes a significant amount of the stress off of these points of concern. So I think that's probably one of the biggest reasons we've had such good success with this hub, is that we've been using it in the shock cord to dissipate some of that energy.
Okay, yeah, we'll take a look at a couple of items on the tripod maintenance. This tripod, it's actually the tripod I bought with the FMJ antenna, and I think there's probably been some modifications to the tripods over the years, but I'm not too sure what they are. But what this is is the underside of the tripod base, and the way it attaches the mounting nut to the tripod base is using this appears to be a stainless steel springed plate that's kind of bowed, and what you do is you tighten this nut, the bolt here, down so you get a good friction fit with the top of the base, and it holds the pedestal steady where you screw the hub in. I've had these things get loose, and you just want to check them once in a while and make sure you snug them up. You don't want to tighten it up so much that you flatten out that plate, because that'll take the spring effect out of it, but that's just something you need to occasionally keep an eye on. And then these bolts, it doesn't hurt to give them a touch with a wrench every once in a while. I don't recall finding anything extremely loose, but it's still good to touch it up. So that's just a little bit on the tripod maintenance. Other than that, the tripod's just been flawless. It's done very well for us. Now take a look at the Hextenna hub, and this is the bottom of it. This is the bolt that screws into the tripod. And one maintenance area you need to keep an eye on, particularly running this loose like we do with the shock cord, is this bolt will, or this nut will loosen, and you want to make sure that you can keep that snug, and you don't want to get on there and just crank a wrench on it. What you want to do is take the cover off and put a wrench on the inside bolt here, that's on the inside, and then use another wrench to tighten it up. And again, you don't want to torque it down so hard that you're going to crack something. You just need to make it snug. So that's the bolt attachment. You can see they've got a big washer here trying to strengthen that area because they recognize that that's a stress concentration point. And here's the cable connector and the counterpoise connector here. The other side of it, this is it's very well marked, so you know what each side of the hub is for. This is the dipole element 1 connection. This would be the vertical connection, and then the other dipole connections on this side. So you can see these lines. It appears to me, I'm pretty sure this was manufactured using 3D printing of some sort, and it's nice, big, beefy box, and it's held up pretty well for us. Here's this shot with the hub open, and I know the first time I opened this, I was a little surprised there's nothing in it other than interconnections, and which makes sense with it just being an actual dipole. But what you have here is kind of a zoom in. This is your center conductor coming from the cable, and it goes to one element and then the vertical element, and then the shield's brought in over here to the counterpoise connection, and then it's jumpered to the other dipole element connection. Everything in here, I like things I like in here. That it's very well wired. You know, nice, neat job. Heavy gauge wire. I really like these shiny solder joints. Those are well done. It's just a good, solid design and assembly. You can change, for example, these elements here, and I did have one of these nuts. The threads wore out, and I was having trouble engaging the Hextenna element into here. So I just actually what I did, since I've never used this one, is I just swapped this nut with this one, and then worked out pretty well. I like the fact that it appears that these are non-hardened nuts, and if you look at the ends of the antenna elements, they appear to be I think they're stainless steel with some sort of thermal hardening process, and so what that does is it since this is soft relative to the threads on the element, this cheap hex nut will wear, whereas your threads on your element stay in good shape. So that's a good design feature. I'm pretty sure they did that intentionally. And I think that's about it. If you, for example, want to tighten the bottom here, say if this is, we talked about this nut getting loose, this is the way you would do it. You'd open this up, put a 9/16 wrench on this one, and then snug it up with another 9/16 inch wrench on this end. And I think that's about all there is to say about that. It's just a well designed, well made piece of gear. Now I want to talk a little bit about the elements and how you attach them to the hub. A couple of things to know. One is because we use the length of the elements to tune the antenna, it doesn't really matter where you measure the length of the elements. I mean, you could measure from this point or this point or this point, as long as you always measure from that point. Now, the convention I use is I measure from this point right here, where the element screws into the hub, and that's just good repeatability. It's easy to click the little clip on the tape measure here to kind of hold it. The other thing to note is that you want to make sure when you're tightening these elements, the way I do it is I'll use one hand and hold the element up because I have it fully extended, and then I use the other hand to screw the element in. And what you can do is you can feel how that thread is going into the hub, and you can adjust the angle that you hold the element so you get no resistance on or very little resistance on the threading, and that tells you you're taking it in a straight line like you need to be. And then you need to watch for is that you need this thread, or the thread all the way till this bottoms out. What you don't want is something like this over here where you haven't quite got it threaded in. A couple of problems there. One, there's a degradation of the electrical connection if it's just kind of catching a few threads there. The other thing is with the motion of the elements in the breeze, you're going to stress this threaded rod coming out of the end of the element, and it can cause problems. It'll cause excessive wear inside the nut, and could break the threaded end of the element off. So you want to make sure that that bottoms out each time to help protect your antenna. And that's about all I know. If you're interested in the Hextenna, we have several videos in our Ham Group's YouTube page. All you have to do is search our call sign, KC3TL. We have Hextenna videos and a lot of other videos that these are videos that we put together for our technical talks at each of our monthly meetings. So if you have any questions, let me know, and we'll see you next time. So 73, this is K3SKS.